Yeah, that's,
we would address that off skid. And as you see this and on skids, so yes, we would. There's some analysis that goes on with each application to make sure that the big chunks are out of the way before they hit the membrane.
Little chunks don't mess up with the interface of the.
Yeah, I mean, we typically the onboard filtration is typically between 1 and 6 micron. So it's
you most likely have a pre-filled.
we do.
Right.
But essentially, yeah, obviously, yeah, if you're under a 20 micron or a 50 micron particle, it's not going to hang up in there. It will go down. There is a concern that if you start getting particles damaging the surface, you're going to interfere with the moisture exchange rates. And part of that's why we've built in a pre-filter right into the skid. So essentially, it's we like to call it a very simple, very elegant solution that we've taken all the complexity of things like vacuum purifiers and centrifuges out, developed a very, well, now it appears simple, very technical dehydration contactor that goes in the middle, and that drives the whole process. So we've got a cutaway view of how the system works here. I think I already covered all these. One thing that is interesting, yeah, we talked about saturation point a little bit. There is no concern with that with us. Essentially, the greater the differential between the moisture in the air and the moisture in the oil, the greater the rate of exchange. And that's why if you have a system that upsets periodically, like the example I gave of that other power plant, that every time they change load, this thing will take out when that thing loaded up like that, the rate of water removal is 10 times higher than it is when it gets down to 100 ppm again. So it goes up with the concentration. Diffusion, yes, that's all it is. So, basically in operation, the unit typically is installed as a kidney loop or a slipstream to the reservoir. We'll take oil right off the bottom drain, that's fine. So essentially we'll have, the skid has its own pump, so starting on the upper right, we'll essentially hook into the reservoir, again dump somewhere low. We're using a gear pump to essentially pull the oil out. First thing it sees on the skid is a particle filter. And this is the one, like I said, you can adjust it to meet your needs. What we recommend to people is the flow rate challenge on this filter is very low compared to your full flow filters. You think this filter's got enough surface area to handle 200 or 300 gallons a minute of oil. We're going to give it 8 to 16 or 30 gallons a minute of oil. Because of that, there's no load challenge on the filter. It's got what we call a low flux rate. It's flow rate per unit area. Because that's low, we can generally help people unload their full flow filtration needs. As an example, the paper mills that we do a lot of work in Minnesota with, they'll run 4 6x39-inch cartridges at several hundred gallons a minute, and then change them 4 times a year at 500 milliliters, so that adds up to 100,000 a year. By putting in one large filter at extremely low flow rate, we unloaded those filters. They no longer plug. We take all the contaminants, and they plug 2 of ours, which are half the price. So we essentially knock 75% of their straight filtration expenses by doing it down at an optimized level, at a very low flux rate. And that's where here, at a bare minimum, we'll match it sort of to your plant. Power plants, what, 6 micron probably, maybe 12. We can go to that level. Paper mill, that one, just in that example, they went to 1 micron. Why not? They can afford to do it that way. So essentially, we're removing all the all the solid contaminants. The oil then flows into the dehydration housing. Like I said, and that's essentially a horizontal housing. It could hold either 1, 3, 7, or 14 of those modules in parallel. So depending how much dehydration capacity, how much oil capacity you have, you scale it up and down as needed. The oil then basically goes in one end of the contactor, out the other, and back to the reservoir. And then on the inlet side, we're taking plant air. We make what's called a stealth air dryer. And that's essentially, it's a hollow fiber membrane as well. And that's essentially a point-of-use membrane air dryer. We'll take plant air. We try and work with process air as opposed to instrument air because of cost issues. So we'll take process air, dehydrate it down to 40 below with an air dryer, and then introduce it into the system. Since the air goes in completely dry, it actually comes out really dry. You know, it went in at a 40 below dew point. When the oil is getting cleaned down into, say, 50 parts per million water left, down just to the discrete dissolve, the amount of moisture coming out of the air is extremely low. So it comes in at -40, it might come out at -25. You can vent that right in the room. You know, until you got up to +60, you're not going to condense water. So it essentially is dry air, so you can just let it go. The one thing we don't show on here is built into the base of the pre-filter housing is a online moisture probe. And essentially that's measuring using capacitance to measure the level of dissolved moisture in the oil. And that will give you either a local PLC reading that tells you you're at 50% of saturation or 20% or 100%, and the temperature of the oil at any given moment. So we use that to help people tailor how much air they're burning. So if you know you've upset the system and the meter saying you're saturated, you turn up the air regulator on the inlet here to full flow. Now you let a lot of air through, do a lot of dehydration. As the oil starts to dry, you get down to 50% saturation, you're wasting air. You can cut back. You know, get down to 20%, cut it way back. So essentially we use that to tailor how much you're using.
For that part of the monitor, how low can you go? This capacitive measurement?
10% is probably getting down towards its visibility threshold.
Would it be desirable to go lower? If there's a means of helping you get it down to really low, would that be of some benefit?
I think the people in the room would answer the question better than we would. Personally, I don't know if it's how critical that is to them. You know, the challenge is we're looking at an instrument that, I guess, for one thing, we don't look at it and say, we've calibrated the curve for some people and say if you're at 40%, that means 80 ppm or whatever it really is. You actually have to calibrate it for every single oil, so that's a real nuisance on our end. If someone's running a really premium plant, yeah, I could see that they really want to know that.
Because I didn't talk about, there is a parallel technology with what I presented this morning that can go and measure moisture parts per billion.
In oil or in air?
In oil. In oil.
That might be interesting. I don't know if it fits into this product, but
it's a fiber. That's the point I'm leading to be a continuous monitoring without having sample taken, because when sample are taken, contamination is always introduced.
Yep.
So if it's an inline monitoring, it will be good to sell your product. to illustrate that yes, you guys did the job, right?
Right.
Because,
Sure.
yeah, and that's why but to your point, that's exactly why we're doing it inline, is they can hook this right up, 4 to 20 output, they can hook up to the DCS, and they'll know when the systems are in where they want them, when they're out, much like your graphics are saying. They'll know when they're in target and when they're out of spec. And that's the biggest thing for us. So we use it more as a trend monitor that's saying we've got a lot of water, we've got almost none, and we kind of basically refer to it as air conservation, because when we're really trying to dry oil, we might be running 30 CFM of air, which is measurable. But if you cut that down to 2 CFM when it's getting dry, or a half a CFM in some cases, that's a lot more economical.
Beth mentioned that reducing moisture in the oil could extend bearing life.
Correct.
Would there be any interest to correlate that with vibration measurement of the bearing? Like vibration measurement gives an indication of bearing wear out. So if lower moisture can be correlated to vibration amplitude, it will be another proof that your product is doing.
Correct. We, thus far, haven't seen, because the payback on machinery in certain industries that we've been exposed to thus far might be so extended. We haven't seen that to be an interesting point yet. They haven't drilled down to that because the ROIs are multi-year. I think right now what we're seeing, maybe the case for you as well, but people are always looking at 5-year or less ROI. So unless they have a really catastrophic problem, I'm not so sure how pertinent that is. But it's a very good point for people who have extremely expensive equipment that are doing longevity studies. I mean, it makes a lot of sense.
Yeah. The challenge is on the turbine side itself, on a steam turbine, bearing life is years and years and years. So it's hard to get a quick read.
Going back. Don't get off of that.
Don't move.
How much? I was looking at that thing and I wasn't paying attention to what you said. How much volume is? How much flow rate does this take?
The oil flow set?